at the left side of the forward fuselage and continues in a clockwise direction around the airplane. From the main entry door, move forward toward the nose of the airplane and check that the pitot covers have been removed. Ensure that the pitot head has not been damaged and is unobstructed. Check the condition of the upper and lower static ports. The plugs should be removed and the static ports unobstructed. Check the windshield for damage such as crazing, cracks, or delamination. While viewing the windshield, check to ensure that the windshield wiper arm and blade are in good condition. Looking slightly forward of the windshield, check that the windshield de-ice fluid discharge nozzle is not damaged. Slightly aft of the radome, check to be sure that the air temperature probe is undamaged, secure, and clean. Looking slightly forward of the air temperature probe, notice the ice detector. Rotate the ice detector by hand and check for freedom of movement. Check the cutter for damage. While rotating the ice detector, make sure your fingers are clear of the cutter. Check to ensure that the radome is secure, that it is not damaged, and that the static discharge strips are properly fastened. Check the nose landing gear doors for security and for any damage or obstruction that would interfere with the door operation. While checking the doors, make sure to check each taxi light for cleanliness, damage, and security. Kneel down and check the wheel well for loose articles, obstructions, damage, or hydraulic leaks. While kneeling in the nose wheel well and facing aft, look to the right and check the auxiliary hydraulic system reservoir. Check for hydraulic leaks and security. Check that fluid is visible in the level indicator tube of the reservoir. It should be full. While facing aft, look to the left of the nose wheel well and check that the pressurization dump valve outlet is clear of any obstructions. Facing aft and looking up into the wheel well, ensure that the gear pin has been removed. If the gear pin has not been removed, remove it at this time. Ensure that the nose steering disconnect pin is correctly installed. If the disconnect pin was not installed, install it at this time. The pin should be inserted from the bottom of the fitting. It is secured by a pip pin inserted from the front. Now check the oleo strut. Make sure it is clean, undamaged, and not leaking fluid. Check that the strut extension is normal for the airplane load. If the strut is below normal, have it serviced. Inspecting the wheels and tires, check that the wheels are not damaged. Check the tires for proper pressure, cuts, or bulges, tread separation, and creep marks aligned with the wheels. Check the chine for separation or damage. After checking the nose gear assembly, move to the forward right side of the fuselage. Check the upper and lower static ports. Ensure that the ports are unobstructed. Step back and check the windshield and the wiper arm and blade. Now check the condition of the pitot head. Check the air data probe to be sure the cover is removed and that there is no damage or obstruction. Continuing aft on the right side of the fuselage, check the condition of the angle of attack probe. Ensure that the cover has been removed and that the rotor is free. Check that there is no obstruction of the fuselage venturi outlet. While standing at the right wing root, check the condition of the wing leading edge inspection light. Check that the lens is clean, undamaged, and secured. Bend down and check that the emergency exit light assembly is secure, clean, and not damaged. At the wing fuselage fairing, check that the methanol tank is full, the filler cap is secured, and the access panel door is closed and locked. After refueling and before the first flight of the day, operate the water drain valves in the wing surface. Using the proper drain container, operate the drain valve to ensure that all water has been removed from the wing tank. Moving outboard from the wing root and looking up at the fuselage, Check that the emergency exit escape hatch is closed and flush with the side of the fuselage. An emergency exit light assembly is located just below the emergency exit hatch on the fuselage. Make sure the lens is clean, secure, and not damaged. After checking the emergency exit, look up at the ram air intake to ensure that the cover has been removed and that the intake is not obstructed. Look up at the top of the vertical fin for the anti-collision light assembly. Check the condition of the lens. It should be clean, secure, and not damaged. Looking aft toward the vertical fin, check to ensure that the HF antenna is secure, not damaged, and correctly tensioned. Standing at the wing root and facing aft, check the right engine inlet to ensure that it is free from foreign objects, clean, and not damaged. Check the engine fan blades for damage. Check the inlet sensor to make sure it is clean and not damaged. Standing at the leading edge of the right wing, check the top surface of the wing for any foreign material or damage. Turn and walk outboard towards the wingtip and check the leading edges for security of the distribution panels and the presence of de-icing fluid. Check the condition of the landing and taxi light. Ensure that the transparent covers over the lights are undamaged, secure, and clean. A stall strip is located just outboard of the landing and taxi light assembly. Check it for damage and security. Continuing along the leading edge of the wing, check the condition of the fence on the upper surface. Check for damage and security. Check that the fuel cap is closed and locked. Now check the undersurface of the wing. Make sure all access plates are secure and that there are no fuel leaks. Check to ensure that the stall vent plug has been removed and that the vent is not obstructed. Moving outboard to the wing tip, ensure that the navigation and strobe light cover is clean, secure, and undamaged. Standing at the wing tip, check to make sure that the static wick is secure and undamaged. While at the wingtip, kneel down and check that the fuel tank vent intake is secure and unobstructed. Operate the water drain valve next to the vent intake using the drain container. Ensure that all water has been removed from the fuel vent surge tank. Make sure the aileron fence just outboard of the surge tank is secure and not damaged. Now move to the trailing edge of the wing. Check to ensure that the static wicks are secure and not damaged. Continue walking inboard along the trailing edge of the wing and check the aileron and tabs for damage and security. Check that the shrouds are free from foreign objects. Moving further inboard, check the condition of the flap surface. Check that the drain holes on the inboard section of the flap are clear. Standing at the trailing edge of the flap, check the condition of air brakes on the upper and lower surface of the wing. Moving further inboard, check the fairing and main landing gear door for security and any damage. Check the condition of the hydraulic actuator on the gear door. Check the condition of the wheel well. While inspecting the wheel well, check to ensure that the gear pin has been removed. If not, remove the gear pin at this time. Next, check the oleo strut and brake hoses to make sure they are secure, undamaged, and not leaking. Next, check the tire and wheel assemblies for damage. Moving aft of the gear to the lower fuselage, use the fuel drain container to make sure all water has been removed from the ventral fuel tank. Check the keel beam area for the anti-collision light. Check that the light is clean, secure, and not damaged. Also check that all antennas are secure and undamaged. Continue aft along the fuselage to the right engine. Ensure that the cowlings are undamaged, fasteners are secure, and all vents are clear. Look for evidence of engine oil, fuel, or hydraulic leaks. Check that the starter generator cooling air inlet and outlet ducts on the bottom of the engine cowling are clear. A carbon deposit may be found in the area of the outlet, particularly if an oil film is present. The deposit, caused by normal brush wear, can be accepted as normal. Check that the engine fuel and oil drains are clear. Check the engine oil for the proper level. Engine oil should be checked daily or every 6 hours of flight time. Check the oil filter bypass indicator pin. It should not be extended. If the pin is extended, call maintenance. Check that the turbine exhaust cover is removed and check that the tailpipe is clear of loose articles, undamaged and dry. Examine the general condition of the rear turbine blades. After inspecting the right engine, move to the rear equipment bay access door. Open the rear equipment bay access door. Disconnect the duct extension by removing the pip pin. Check to ensure that the door is not damaged. Standing up in the equipment bay and facing aft, check that all access panels are in place and secured. Check to ensure that all loose equipment has been removed. Check the general condition of all the air ducts. Check the condition of the batteries. They should be secured properly and not damaged. Check the main hydraulic system reservoir for signs of leaks. Make sure the filler cap is closed and locked. Check that the hydraulic reservoir LP doll's eye indicator shows black. Check the reservoir for the proper fluid level. The fluid level shown in the fluid indicator tube varies with system pressure. Compare the fluid level in the indicator tube with the appropriate marking on the adjacent label. Continuing to the right, check the hydraulic accumulators for proper pressure. 950 psi is the minimum. 1,750 psi is required on the emergency accumulator for parking brake operation. If emergency accumulator pressure is not sufficient, use the ground service hand pump to build up the pressure. Facing forward and looking to the right, check the APU fire bottle pressure indicator. The indicator should be in the green band. After completing the inspection, reinstall the pip pin in the duct extension and close and lock the equipment bay access door. After securing the aft equipment bay door, move to the right rear fuselage access panel is closed and locked. Also check that the ventral fuel tank filler cap is closed and locked. If external power is not being used, make sure that the access door is closed. Now step back and look up. Just above the engine mounting fillet, check that the APU exhaust opening is not obstructed. Move to the tail section and check the condition of the tail cone. The cover should be removed and the access panels closed and locked. Check that the strobe light is clean, undamaged, and secured. Standing by the tail area, look straight up and check that the white navigation light is clean, secure, and not damaged. Moving to the right side of the vertical stabilizer, check the leading edge distribution panels for condition. Check for evidence of de-icing fluid. With the rudder centered, check that the trim tab and anti-servo tab are in the neutral position. Check the condition of the static wicks. Looking up at the leading edge of the right horizontal stabilizer, make sure that the distribution panels are secured and not damaged. Also check for evidence of de-icing fluid at the distribution panel. Check the elevator for damage and security. With the elevator down and a neutral trim setting, the trim tab is slightly above the trailing edge of the elevator. Check the static wicks on the tip and trailing edge of the elevator. Now move to the left side of the tail assembly. Check the static wicks on the trailing edge and tip of the elevator. Also, check the elevator for damage and security. Check the left horizontal stabilizer leading edge for damage. Inspect the left side of the leading edge of the vertical stabilizer for security of the distribution panels and the presence of de-icing fluid. Check the rudder for damage, security, and the condition of the tabs. Now move from the tail area to the left rear fuselage. Check that the oxygen recharging access panel is closed and locked. Check that the fire extinguisher bottle discharge indicator for each engine shows a green disc. Step away from the fuselage and look above the engine mounting fillet. Check that the intake opening for the APU is unobstructed. Check that the turbine exhaust cover is removed. Ensure that the tailpipe is clear of loose articles and dry. Check for any damage to the turbine blades. Moving from the exhaust area to the side of the engine, check that the cowlings are undamaged, fasteners secure, and all vents are clear. Look for evidence of leaks. Check that the starter generator cooling air inlet and outlet ducts on the bottom of the engine cowling are clear. Check engine fuel and oil drains. Move to the inboard side of the engine and check the oil level. Check the oil filter bypass indicator pin. After completing the inspection of the left engine, move to the left main gear. Check the fairing and main landing gear door for security and damage. After checking the fairing and door, look up into the wheel well for any loose articles, hydraulic leaks, or obstructions. Check to ensure that the gear pin has been removed. If not, remove it at this time. Now check the main gear oleo strut and the brake hoses to make sure they are secure and not damaged. Check both tires and wheels for any damage. Moving to the trailing edge of the wing, check the condition of the air brakes on the upper and lower surfaces of the wing. Moving outboard along the trailing edge of the wing, check the flap surface for damage and security. Ensure that the flap drain holes are clear. Continuing outboard, check the aileron and tabs. Check that the static wicks are secure and not damaged. Moving to the wing tip, make sure the static wick is secure and not damaged. Check the fuel tank vent intake. Also, check the aileron fence. Now, operate the water drain valve in the surge tank. Check for water. Moving around the wing tip to the leading edge of the wing, check the navigation and strobe lights. While moving inboard along the leading edge of the wing, check the upper surface of the wing. Continuing inboard, check that the fuel filler cap is closed and locked. Check the fence on the upper surface of the wing. Check the underside of the wing. Check the stall vents. Continue walking inboard. Check the leading edge distribution panels. Moving further inboard, check the stall strip. Check the landing and taxi lights. Moving inboard to the wing root and looking aft at the left engine, ensure that the inlet plug has been removed. Check the fan blades and the inlet sensor. While at the wing root, check the wing leading edge inspection light. While kneeling down just below the wing root, use the drain container to operate the drain valve. Ensure that all water has been removed from the wing tank. Now that the exterior pre-flight is complete, return to the cabin to complete the interior inspection.
APU start. LP cock open. Left boost pump to emergency. Light out. Master switch on. Test annunciator lights. Test fire warning. Turbine start switch, push. Parameters have stabilized. We have a successful start. Test EGT warning. Test overspeed warning. Generator on. Bleed air on. Start complete. APU start. Left LP cock open. Left boost pump to emergency. Light out. Master switch on. Annunciator test. Fire warning test. Start button push. Over temp. Master switch off. Master switch back on to monitor spool down. Abort procedure complete. Master switch off.
Standby inverter coming on, arm light on, XE fail light out. XE bus voltage 115, frequency 400. Inverter number 2 on. All lights out except inverter fail 1, XE bus 115, frequency 400. Inverter number 2 off. All lights back on. Inverter number 1 on. Lights out except for inverter 2 fail. XE bus voltage 115, frequency 400. Inverter 1 off. Lights back on. Standby inverter operating. Inverter 1 and 2 on. All lights out. Inverter check complete.
Overhead test panel functions. We're going to start out by testing the fire warning systems, the pylon overheat warning, the high pressure overheat warning, the stall warning channels, the air data computer check, cabin altitude warning, ice detector warning, and VMO, MMO warning. I'm going to check the fire detection system check by first isolating the bells and pushing fire system number 1's test button. I should see an engine fire 1 annunciator light up in the fire warning panel. The master warning light should flash. I'll see a red warning repeater light shine down on the pedestal. I'll now go up and de-isolate bell number 1, and I should hear the bell. I'll repeat the process for fire detection channel number 2. Push the switch, engine fire number 2 warning light, master warning flasher, engine number 2 fire warning repeater, and de-isolate bell for number 2 channel. Now we'll test the pylon overheat warning lights on the master warning panel. Master warning light flashing, and both pylon overheat warning lights should test. Next test will be for the high pressure overheat warning lights. Master warning flasher, high pressure overheat warning lights. Now we'll check each one of the stall detection systems. We'll check the left system first. I'll push the button and we should hear the stick shaker operate. I'll do the same thing for channel number 2 or the right side. Now with no fuel in the auxiliary tanks, pressing the low VMO 1 and 2 channels will give us an air data computer check on the left and the right panels. Next check will be the cabin altitude warning. This will turn on a red cabin altitude warning light, the master warning flasher, and a warning horn, which will be silenced with the horn isolate button in the left-hand throttle. The ice detector test will test the ice detection system by turning on an ice detection warning light. The overspeed horn test will test the normal overspeed warning horn functions for the left and right pitot-static systems. Left first, right second. This completes the test of the overhead test panel.
Okay, pre-start checklist. LP cocks open, HP cock closed, computers to auto, boost pumps on, lights are out, nav is on, beacon is on. Start checklist.
LP cocks
Are open,
HP cocks,
closed,
computers,
auto,
boost pumps.
on.
Checklist complete.
Okay, ready to start. All clear right.
Clear right.
Start power available. Start operating. Into rotation, 10%.
Okay, we got fan rotation,
Okay, 15%. Fuel on. Got a light off.
ignition, oil pressure's rising, oil pressure lights out, hydraulic pressure's up.
Okay, looks like a good engine. We've got fuel flow, 31%, 500 degrees, 60%. Oil pressure's good. Good, and the ignition is off. Power off. Okay, pre-start. LP cocks are open, HP cocks are closed, computers auto, booster pumps on, the lights are out, nav and beacons on. Pre-start checklist.
LP cocks,
Are open,
HP cocks,
are closed,
computers,
auto,
boost pumps.
on, lights out.
Checklist complete.
Okay, ready to start.
Clear
number
right.
2. Clear and ride. Okay. Start power available. Start operating. 10% into. All fan speed.
Fan
please.
speed,
15%. Fuel on. Got a light off.
hot start.
Looking hot. HP cock closed. Starter aboard. APR check. APR is armed. 5% increase in N2. Right engine increases. APR disarmed. APR armed. Right N2 increasing 5%. APR triggers. Left engine increases. Power to idle. APR disarmed. APR armed. APR override. Both engines increasing. Override off. APR arming off. APR armed. Override light out. APR disarmed. APR check complete. Computer check. Guard the number 1 HP cock, Jim. If you see a problem with this engine running away, stop cock the engine.
Okay.
And computer go into manual. The engine is stable. Computer light is on. Power increase. Into increasing. ITT increasing. Power decrease. Computer to auto. Light is out. And engine is stable. Okay, guard number 2 HP cock, if you would.
Number 2 guarded.
Number 2 computer to manual. Engine stabilizes. Computer fail light is on. Number 2 engine responds to power lever increase. And responds to power lever decrease. Computer to auto. Light is out. Engine is stabilized. Computer check is complete. Start power off. Left and right pit of heat on and checked. Alternator 1 and 2 on. Windscreen heat 1 and 2 on. Bus tie check.
Bus tie open. Check voltage on PS1. And PS2. Voltmeter back to PE selection. Bus tie switch closed. Bus tie generator check complete.
Rudder bias check. Rudder bias is off.
Guards lifted, rudder bias off.
And rudder bias fail light is on. Engine number 1 coming to 65% N1. Rudder bias A on.
Rudder bias A on.
And we get a rudder deflection. Rudder bias A off.
Rudder bias A off.
Rudder bias B on.
Rudder bias B on.
And we get a rudder deflection in the same direction. Rudder bias B off.
Rudder bias B off.
Okay, we'll try the right engine. Power coming to 65% N1. Rudder bias A on.
Rudder bias A on.
And a rudder deflection. Rudder bias A off.
Rudder bias A off.
And rudder bias B on.
Rudder bias B on.
We got a rudder deflection. Rudder bias B off.
Rudder bias B off.
Power to idle. Rudder bias A and B on and guarded.
Rudder bias A and B are on. Guards are closed.
Okay, and the warning light is out.
Center, Hawker 125, requesting lower. Center, Hawker 125, requesting lower. I got electrical malfunction. Bus tie's open.
Okay, bus tie open. Check PS1 and PS2 voltage.
PS2 normal. PS1 shows over 30.
Okay, let's get the abnormal checklist voltage out.
Yes, sir. Abnormal voltage checklist. Here it goes. Abnormal voltage, PS1 and PS2. Check, identify faulty generator. It looks like number 1 generator to me.
I agree with that, Jim.
Okay, affected generator, trip. Things are going to get dark here for a second.
Okay.
Number 1 generator's trip. Bus tie closed. Bus tie is closed. Electrical loads are under 200 amps, so they're well within limits. And I'm going to reset the number 1 inverter. Checklist complete.
Identify what the problem is up there, Jim.
We have failures on generators 1 and 2, inverters 1 and 2.
Then try a reset on those generators, will you?
I'll try to reset number 2 first. Number 2 won't reset. Let me try number 1. Number 1 not resetting either, sir.
Okay, double generator checklist, panel lights to emergency, battery switch to emergency,
Battery switch going to emergency. In emergency.
standby inverter to on.
Standby inverter is on. XE failure light is out.
Okay, check the bus voltage.
PE bus voltage is 25.
And the XE.
XE bus voltage is 115.
Okay, fine. Double generator checklist.
Yes, sir.
Double generator fail checklist.
An electrical repeater.
What's our problem?
Battery is hot.
Battery hot. Check the charge on battery 1 and 2, please.
Battery charge is near 0.
No, okay, check the battery temperature gauge. See what
They're both going through 160 degrees.
160 degrees. Okay.
Now we have a battery overheat warning.
Okay, battery overheat. Let's select battery switch to emergency.
Battery switch going to emergency. Selected.
And, battery overheat checklist.
Okay, battery overheat checklist coming up. Houston Center, Hawker 125 requesting lower.
Hawker 125, Houston Center, descend and maintain 6,000. Altimeter setting 2992.
Hawker 125, leaving 10 for 6. Hawker 125, leaving 10 for 6.
Isolate the bell, please.
Hey, bell's isolated.
Tell Center we're going to stay here for a couple minutes.
Houston Center, Hawker 125, we've got a small problem. We're going to stay at 10,000 feet. We'll let you know.
Okay, what have we
Number
got?
2 engine fire indicated here.
Okay, number 2 engine to idle.
Number 2 throttle. Idle.
Okay, number 2 HP cock.
Number 2 HP cock shut.
Number 2 LP cock.
Number 2 LP cock shut.
Fire shot 1.
Okay, firing shot 1. Shot 1 fired.
Okay, and engine fire checklist, please.
Yes, sir. Engine fire checklist. Power set.
Fire set.
APR armed. Time started. Airspeed live. $80 knots.
IO.
Power set.
Fire set.
APR armed. Time started. Airspeed live. $80 knots.
IO. Abort. Flaps.
Full flaps. Right engine's pulling down.
Your yoke.
I have the yoke. You have liftoff.
APR armed.
Set. APR is armed. Time started. Airspeed live. $80 knots.
IO.
Your yoke. B1 rotate. APR is armed. Time started. Airspeed live. Knots.
I yoke.
Your yoke. V1, rotate.
APR override.
APR is overridden. Positive rate.
Gear up.
Gear is selected up.
Air valves closed.
Air valves closed.
Okay, identify our problem, if you would, Jim.
Okay, the right engine has pulled down.
Okay.
I'm going to identify it by pulling the right throttle back. Right engine failure confirmed.
Okay.
1 minute and 20 seconds into the climb.
Advise me to 3.5 minutes or 1,500 feet, whichever
Yes,
comes
sir.
first.
3 minutes, 15 seconds.
Okay.
3 minutes, 20 seconds.
The altitude hold on the command bars, please.
Altitude hold selected, 3 minutes, 30 seconds.
V2 plus 6, gear or flap retract.
V2 plus 6 confirmed, flaps coming up. Flaps retracted. Minutes into the climb. 4 minutes, 50 seconds.
Okay. APR disarmed.
APR disarmed. Standing by.
885 on the tip.
885, max continuous power. Max continuous power set.
Engine fail checklist.
Engine failure checklist. Right engine's rolling back.
Roger. Compare right engine to idle.
Okay, right engine coming back to idle.
Immediate relight drill. Mission on. Cancel the master warning.
Master warning canceled. Immediate relight doesn't seem to be having any effect, sir. It's still rolling back.
Okay, let's do our shutdown on the right engine. Sir?
Okay, right engine confirmed. It is rolled back.
Okay, let's do right engine shutdown.
Okay, HP cock. Off. Right LP cock. Off. Synchronizer. Off. Main air valve closed. Right generator tripped. Bus ties closed.
And the remainder of the checklist in your own time.
All right. Right engine rollback.
I concur, right engine, immediate relight valve.
Okay.
Right throttle.
Throttle to idle.
Ignition on.
Ignition on.
Cancel the warning.
Warning canceled. Engine's coming back, sir.
And what was our problem? Let's go anti-ice, engine anti-ice on both engines.
Engine anti-ice on both engines.
Okay.
We're stabilized at idle on the right engine.
See any reason for that rollback then?
No, sir. We're about +6 on the temperature outside. I couldn't see any reason for that to roll back.
Let's try normal power.
Okay, advancing the power. The engine has responded. Power's matched.
Do you see any reason why we shouldn't try a restart on that engine, Jim?
No, it just looked like there wasn't any mechanical difficulties to me. I think we can start this up. Want to give it a try?
-4.
We're showing +5 indicated.
Turn the ignition off on that number 2 engine. Okay, let's try a air start on that. Air start checklist.
Okay, air start checklist. I'll call out the items to you as I do them. That'd be all right. Hey, windmilling or starter assisted relay, speed and altitude. Check with an envelope. We're at 10,000 feet and 220 knots. That puts us very solidly within the starter assisted relay envelope and out of the windmill.
Okay.
Relay envelope. N1 and N2, check indicating. N1 and N2 are indicating.
Roger, I agree.
HP cock confirmed shut on the right engine. LP cock confirmed open on the right engine.
Okay.
Engine anti-ice confirmed off on the right engine. Fuel pump confirmed on. Synchronizer confirmed off. Main air valve confirmed closed. Check N2 RPM below 15%. master, so I proceed
Let's go
with
starter assisted relay.
starter
first.
assist. All right.
Okay.
Start power switch. Pushed, confirmed on. Right starter switch. Pushed. N2 increasing. Right HP cock open. Ignition on, we have light off. Oil pressure is coming up. N1 and N2 accelerating normally. We have a successful start.
Roger, let's match these engines then.
Okay, I'll match the engines.
And continue with the cleanup checklist for the remainder of the checklist. I have the power.
Okay, cleanup checklist to go. Starter switch, light out. Start power switch, light out. Generators, I'm going to open the bus tie.
Okay.
Generators are checked and normal. Bus tie closed. Engine instruments appear to be normal to me, sir.
Looking normal.
Main air valve returning to open. Throttles are set. Cross feed closed. Checklist complete.
Good.
V1 rotate. Positive rate.
You're up.
Gears selected up. V1 rotate. Positive rate.
You're up.
Gears selected up. Now we have a right reverser unlocked indication.
I concur. The right one. Reduce the right power lever to idle.
The right power lever coming back to idle. Right power lever at idle. Lights still on.
Emergency stow.
Reverser stow. Unlocked light is out.
Okay, checklist.
Fire warning.
Isolate the bell.
Okay, bells won't isolate. Fire warning.
Isolate the bell.
Okay, bells won't isolate. The APU is indicating a fire.
Master off.
Master off.
Wait 10 seconds.
Time started. Within 10 seconds, I'm going to fire the bottle.
Okay.
Fire extinguisher shot. Fire's extinguished, sir.
And let's shut. have right up too high on it. Down to the dam. How about there? See the jump? Oh,
Here we've got a fuel repeater light on.
Would you identify that problem, Jim?
Here we've got engine number 2, low pressure warning.
Low pressure warning. Okay, select the cross-feed valve open.
Cross feed valve open.
Okay, the light should go out.
Low pressure light is out.
Okay, turn off the affected pump.
Okay, the right boost pump is off.
Okay, and fuel low pressure warning light checklist.
Okay, checklist coming up. Captain, we got a filter bypass on the right engine.
Roger.
Would you like me to reduce power and see if we can stop the bypass?
Okay, let's reduce the power a little bit.
All right, calling back on the right engine. I put the light out, sir.
Roger. Checklist for that malfunction.
Okay, fuel filter blockage checklist. Says if flight conditions permit, reduce RPM until warning cancels, which we did. Checklist complete. We got 2 hydraulic low pressure lights.
Okay, check with the system pressure gauge.
System pressure looks to be about 2,300.
2,300 psi. Okay, that indicates that both of our pumps have failed. We have retained 2,300 so that we have our normal brakes with anti-skid. The emergency brake low pressure light is extinguished. Therefore, we have our emergency brakes for a backup if we need.
I agree.
Okay? Let's go and get the hydraulic fail checklist out and see what it says.
Hydraulic failure checklist coming up. Okay, for 2 hydraulic low pressure lights.
Okay,
No crew action until landing gear lowering necessary.
course is alive, so I'm going to turn in.
Okay, localizer is alive.
Carry on with that checklist, huh?
Okay, landing gear emergency lowering requires the emergency undercarriage handle pull, do not
Okay,
reset.
we'll pull that one.
Operate the hand pump until the gear locks down.
Okay, so we need that extension handle in there.
Okay, I have the handle. And finally, landing gear lever down.
Okay, after we get it 3 green
All the way
lights, we'll
down.
extend the landing gear handle. Okay?
Flaps emergency lowering.
Okay.
After lowering the landing gear as detailed above, flap selector set as required
Okay, we'll select.
and operate the hand pump to the selected setting.
Okay.
And that completes the checklist procedure.
Okay, fine then, Jim. I'll expect that you can go ahead and handle the extension of the gear and flaps as I call for them. We'll do a flap 25 approach. We'll use a speed of ref plus 20, so we'll use a 139 for a bug speed.
Okay, 139 will be set right and left.
And our landing distance will be 5,700 feet with our additive. How much landing distance do they have available for us at
We've
Norris?
got 9,228 feet on
Okay,
runway
92,
10.
so we're okay for that then. So we want to get this gear and flaps down early prior to, we'd like to have it all finished up by about 5 miles to the final fix. And
We're
now
about 10 miles out now.
So we'll hurry up and do this and get it done. But at any rate, we'd like to have it all done prior to the final fix. We'll have to land without the benefit of air brakes, lift dump, and nose wheel steering. Okay,
Correct.
so that shouldn't be any problem now. So let's get with extending the gear. Okay?
Okay.
We have been cleared for the approach, so
We are
that's no
cleared.
problem. So I'll just intercept and proceed then.
Okay.
So you can extend the
You're ready.
gear at this time. Ready.
Okay, emergency undercarriage handles pulled.
Okay.
Okay. And I'll pump until the gear is down. Nose gear is down.
And we're still 8 miles from the final fix, so we're in good shape there.
Brake gear is down. Left gear is down.
Okay.
Final step. Landing gear handle down. 3 green, red lights out.
Okay. Concur, let's go. Concur, let's go with flap 15 then.
All right, setting the handle to flaps 15. Flaps are moving. Flaps indicate 15.
Okay. Glide slope is alive, flap 25.
Setting the handle to flaps 25. Flaps are moving. Flaps are 25.
Okay, good. Declaring emergency if you're ready. Close the air valve, open the float exit valve. Air valve's on. Valve open. Declare emergency, don't have this in. Center, Hawker 125. Office pressure is open, declaring an emergency.
Rear bay overheat.
Rear bay overheat. Close the air valves, open the flight deck heat valve, 10 seconds.
Air valves closing. Flight deck heat valves.
Okay, monitors on right.
Flight deck heat valve all the way open.
Does not appear the light is going out.
Yeah, it's been 15 seconds.
Okay, declared emergency, request emergency descent, close that flight deck heat valve.
Walker 125, declared an emergency, pressurization problems, request emergency descent. Flight deck heat valve closing.
Okay. Now we're going down.
Right pylon overheat.
Overheat. Right power lever coming to idle.
Idle.
Right air valve closed.
Right air valve closing. Time started.
We'll give that about 15 seconds, and if it doesn't go out, we'll have to secure that in.
15 seconds.
Okay. Let's secure the right or number 2 engine. I have the number 1 guarded.
Right HP cock closed. Right LP cock closed.
Okay.
Synchronizer off. Right main air valve closed. Right generator trip. Plus tie closed. Ready for the checklist.
Okay, checklist.
The information contained in the following video presentation represents Allied Signal propulsion engines operational recommendations for all models of the Garrett TFE 731-2 and -3 turbofan engines. The material is designed to assist owners and operators in achieving the best possible balance of performance, reliability, and cost-effectiveness from their engines. Allied Signal believes you have access to many sources of information which may influence the operational decisions you make as pilots. In many cases, previous experience is the most reliable and complete source of operational counsel. The material contained in this presentation is the product of our experience gained during the design, testing, and certification of the TFE 731-2 and 3 engines, as well as experience accumulated by operators of many different aircraft models. To the very best of our knowledge, the information is fully compliant with the Aircraft Flight Manual engine operational procedures as published for aircraft powered by the TFE 731-2 and 3 engines. Included in this list is the 1125 Astra, the British Aerospace 125-700 and retrofits, citation models 3 and 6, Falcon 10, Falcon 50, Jetstar 2 and 731 Jetstar, Learjet models 31, 35, 36 and 55, Sabre 65, and Westwind 1124 and 1124A. In all cases, however, the government-approved Aircraft Flight Manual remains the final authority for aircraft operation. This program will explain the TFE 731-2 and -3 engine control systems and will discuss engine power management procedures. We will review the engine thrust function and the methods of determining and setting takeoff, climb, and cruise power. Although all TFE 731 engine operational characteristics are essentially similar, aircraft installations specify differences in engine functions and power management procedures. Again, the examples used in this program are intended to reflect those aircraft fitted with the TFE 731-2 or -3 engines.
There are two commonly used methods for measuring thrust in jet engines: EPR, or engine pressure ratio, and N1, or fan RPM. The Garrett TFE 731 engine uses N1 RPM for thrust measurement. All production TFE 731 engines are subjected to a test stand run to assure each engine produces rated to N1 relationship. For a given air density, thrust is proportional to N1 RPM. As air density changes, thrust produced at a given N1 RPM changes. For example, at sea level, as outside air temperature decreases, air density increases. As air density increases, N1 RPM decreases while providing the same thrust. Flight manuals for TFE 731 powered aircraft specify a means for calculating takeoff N1. This takeoff value essentially represents a minimum indicated N1 for a given set of ambient conditions. Since outside air temperature and pressure altitude affect engine performance, takeoff N1 calculations must obviously take these two important variables into account. Remember, pressure altitude is determined by setting the altimeter to 29.92 inches of mercury, or 1013 HPA, and reading the indicated altitude. Outside air temperature, OAT, on the other hand, can be determined in a variety of ways. However, each method used has potential inaccuracies which need to be recognized. For example, free air temperature gauges are typically subject to errors attributed to the effects of conduction and radiation. Tower temperature, or ATIS, may also be inaccurate due to the location where the measurement is taken and the time elapsed since the last measurement. Reconfirming OAT during taxi with air flowing across the OAT or SAT-TAS probe while ensuring probe heat is not turned on is a reasonable way of eliminating much of the error that might otherwise be introduced into the N1 calculation. Allow a few extra minutes on cold days for OAT indications to stabilize if the aircraft has recently been moved from a warm hangar. Remember, the electronic engine control sets engine speed using a very accurate temperature probe located in the engine inlet. Care should be used to accurately determine outside air temperature and pressure altitude to ensure your calculations result in the correct target N1. The aircraft flight manual tables and charts provide an N1 which represents minimum required takeoff thrust for the ambient conditions. We emphasize minimum as aircraft performance is based upon this value during takeoff, first and second segment climb. Frequently, actual temperature and pressure altitude values will fall between the benchmark values represented in the N1 tables. When this occurs, the actual N1 must be calculated from aircraft flight manual tables or charts using standard interpolation methods. While this may not be considered practical in all instances, remember, rough approximations can introduce errors of up to 2% N1. TFE 731-2 and -3 engines installed on the previously listed aircraft utilize two related types of electronic engine control systems. Most -2 and -3 engines use an electronic engine control, or EEC. Currently, -2B engines and a few military aircraft use a digital electronic engine control, or DEC. While the two units differ in technical detail, both control systems govern N2 RPM, which produces the desired N1 as determined by power lever position, OAT, and pressure altitude. The control system is designed to deliver rated or takeoff thrust at maximum power lever angle, or PLA. However, due to climb power setting requirements on -3B and -3C powered aircraft, the EEC is adjusted to achieve rated takeoff thrust prior to maximum PLA. When operating in the idle position of 20 to 26 degrees PLA, engine RPM is governed by the electronic engine control to provide approximately 225 pounds of thrust. Remember, based upon changes in air density, the actual N1 value at idle may vary from day to day and from airport to airport. As previously mentioned, when takeoff power is set, the engine accelerates to an N1 value which produces minimum required takeoff thrust. The two-spool design of the TFE 731 results in a predictable N1 and ITT overshoot as takeoff power is initially set. The amount of overshoot will vary dependent upon rate of power lever movement and engine trim, but should always be within the aircraft flight manual transient limits. This small overshoot is not detrimental to the engine. The basic power setting procedures we've discussed apply to all TFE 731 engines. Now let's take a look at TFE 731-2 and -3 systems and procedures, beginning with an engine start. When initiating the start sequence, monitor smooth N2 acceleration. As the N2 RPM passes through 10 to 15%, note an initial rise in N1. Move the power lever, or HP cock, from cutoff to idle position. Observe an initial ITT rise within 10 seconds. Waiting for a positive N1 indication prior to bringing the power lever out of cutoff is a recent change to the recommended starting procedures for all TFE 731 engines and is intended to prevent the crew from proceeding with a start in the absence of N1 rotation. Starting with a locked N1 can very quickly result in significant engine damage. Since repairs can be extensive, pilots are encouraged to check the N1 rotor for freedom of rotation during pre-flight. Within approximately 10 seconds of initial ITT rise, observe an oil pressure indication. Continue to monitor normal N2 and N1 rate of rise and ITT within limits. Be prepared to terminate the start if an abnormality is detected. As the N2 RPM reaches approximately 45 to 50%, note the ignition and, if equipped, starter engaged lights extinguish. N1, N2, and ITT should stabilize as the engine reaches normal idle values. With the engine stabilized at idle, observe that engine instruments and warning lights are normal. Remember, as ambient conditions vary, so may engine starting characteristics and idle RPM. At idle, the anti-ice system can be tested in accordance with the aircraft flight manual. A slight increase in idle ITT with bleed air extraction is typical. On some aircraft, engine RPM may need to be increased above idle power for proper anti-ice system indication. Accomplish a manual mode test of the engine control system to confirm appropriate engine response and computer warning light operation. Switching the control to manual or off position will cause a change in N1 RPM, since the engine is now being controlled by a mechanical governor and the surge bleed valve is 1/3 open. Depending upon ambient conditions, engine RPM should stabilize between 20 and 40% N1. Move the power lever sufficiently, 10 to 15% N1, to demonstrate that engine RPM will increase when the power lever is advanced and decrease when the power lever is retarded. Place the control switch back in the auto or on position, and the corresponding computer light should extinguish. Another feature incorporated in several TFE 731-3 powered aircraft is Automatic Performance Reserve, or APR. When armed for takeoff, should there be a power loss on one engine of more than 5% N2, APR will automatically increase power on the remaining operating engine approximately 1% N2 and 22 to 26 degrees C ITT. Note, there will be no increase in thrust if the ambient conditions are such that the engines are N1 RPM limited during takeoff. In other words, if takeoff target N1 for a -3R engine is 101.5%, there will be no thrust increase if APR is activated due to power loss on one engine. If takeoff and initial climb calculations are based on APR power being available, the system must be serviceable and armed for takeoff, unless the appropriate charts found in the approved takeoff performance with APR inoperative. Therefore, the system must be tested prior to each takeoff. The test procedure is typically found in the Normal Procedures section of the AFM and is accomplished in the following manner. With both power levers set to the idle position, note the N2 idle RPM. Depress the APR arm switch to arm the system. The APR arm light should illuminate while the APR light should be off. Advance one power lever and check that the APR annunciator light illuminates when a differential of about 5% N2 is indicated. Return the power lever to idle. Note the stabilized N2 RPM for both engines. Depress the APR arm switch to deactivate the system. Both engine N2 speeds should decrease by approximately 1%. Check that the APR and APR arm lights are extinguished. A good procedure is to alternate engines on each successive APR check. At certain low idle conditions, you may occasionally observe a slight fluctuation in N1 RPM of 1 to 3%. This occurs normally at low fuel flow rates, has no effect upon engine operation or safety, and does not require maintenance attention. It is characteristic of the flow divider cycling open and closed, routing fuel to the primary and secondary fuel nozzles and causing the RPM to wander in response. Moving the power lever forward to a slightly higher RPM will increase the fuel flow above the crack point of the flow divider and typically stop the cycling. We mentioned reconfirming takeoff N1 calculations during taxi. With airflow over the OAT or SAT probes, they become a more reliable source and may eliminate some of the inaccuracies of static measurements. However, minor differences between calculated and observed target N1 can occur on takeoff roll. Some operating manuals permit a rolling takeoff under certain conditions, but if runway length is limiting, the takeoff should be commenced from a standing start, with takeoff power being attained before the brakes are released. Smooth, conservative power lever movement is recommended. N1 overshoot will be minimized by using the following procedure. Advance the power levers to approximately 80% N1 in 3 to 4 seconds, verifying symmetrical acceleration. Continue advancing the power levers to maximum PLA or, on certain aircraft, target N1 in an additional 3 to 4 seconds. Confirm target N1 is equaled or exceeded by no more than 1 to 1.5%, and if installed, arm APR. Remember, on those aircraft that use maximum PLA, With power levers fully forward, a properly adjusted EEC will control takeoff N1. Further power lever adjustment should not be required as long as engine limits are not exceeded. It's important to understand any time a takeoff is made with the power levers less than fully forward, power lever adjustments may be required during the takeoff roll to maintain minimum target N1. Depending upon the attention devoted to this exercise by the cockpit crew, engine thrust could drift below target prior to rotation. For -3B and -3C powered aircraft, the procedure published in the operational manual recommends setting takeoff N1 at the beginning of the takeoff roll and ensuring N1 has not drooped below target when passing through 60 knots indicated airspeed. Additional power lever adjustments during takeoff roll should not be required. Different techniques in takeoff power management procedures will result in varying responses from the engine. Let's review some of the more common methods and observe the likely effects. Rolling takeoff. Pilots who elect to use takeoff techniques such as early brake release or a rolling takeoff, where power is still being advanced as the aircraft is accelerating, should understand that the takeoff will often be completed and the aircraft well into the climb before engine parameters are fully stabilized. Also, it's important to remember actual runway performance is dependent upon the point at which minimum takeoff power is achieved. As discussed, the flight manual takeoff performance chart is based upon stabilized N1 power prior to brake release. Using procedures other than those outlined in the aircraft flight manual may result in runway and initial climb performance below that specified in the AFM. Reduced power takeoff. If procedures are approved for a specific aircraft type, pilots should refer to the aircraft flight manual for appropriate reduced power takeoff instructions. Since the power levers will not be in the fully forward position during a reduced power takeoff, the following procedure should be used. Set the calculated reduced N1 at the beginning of takeoff roll. Readjust N1 as necessary when passing through approximately 80 knots, verifying N1 has not drooped below target. Never hesitate to advance power levers to full takeoff power at any time during a reduced power takeoff. After the takeoff is completed, set climb power as soon as convenient. This may be after landing gear and flap retraction or after completion of a noise abatement procedure. Although the procedure varies among aircraft models, the following technique is a good target. On -2 powered aircraft, reduce ITT to approximately 800 degrees C, and for -3 powered aircraft, reduce ITT to approximately 845 degrees C, or if a reduced power takeoff was accomplished, maintain that setting. When the recommended climb speed is established, refer to the appropriate aircraft performance charts to obtain a climb power setting for the current altitude and OAT. It is important to understand that during climb and cruise, the N1 and ITT values listed in these charts are maximum power settings, and the engine should be operated at whichever value is most limiting. To compensate for variations in OAT lapse rates during climb, closely monitor N1 and ITT to ensure the values listed in the charts are not exceeded. For aircraft that utilize an ITT or alternate climb schedule, also monitor N1 to avoid exceeding the N1 settings found in the climb power chart. When reestablishing climb after an intermediate level-off, reset climb power per the appropriate N1 chart. If using an ITT climb procedure, reset to the appropriate ITT for the aircraft altitude. For example, an aircraft with -3R engines would be reset to 865 degrees C below 25,000 feet and 885 degrees C above 25,000 feet. It should be noted that maximum climb and maximum cruise operations place the greatest stress on engine components. Power settings that exceed performance manual RPM and ITT values can contribute to the premature replacement of engine components. Therefore, conservatism in climb and cruise power settings will enhance engine durability and reduce maintenance costs. After reaching cruise altitude and accelerating to the desired Mach number, cruise power settings as determined from the performance manual become applicable. Whichever parameter is most limiting, aircraft speed, N1 or ITT should be used. Monitor all engine parameters to be within the normal operating range and consistent with previous flights. Splits in indicated parameters are common and normal. However, progressive increases or decreases in RPM, ITT, or oil temperatures and pressures should be investigated. Also, can a trend be defined? If you note changes occurring over time, a documented record of the indications, a trend, will be of significant value to your service facility. During descents, reduce power slowly to minimize thermal gradients. Use power settings appropriate for pressurization and anti-icing requirements. Cooling period at taxi power is recommended to achieve thermal stabilization prior to engine shutdown. The 2-minute period includes runway rollout and taxi time at idle power.
A more in-depth discussion of TFE 731 engine operation is available upon request. To obtain the latest revision of Functional Training Guide TSG 145 and copies of the TFE 731 Pilot's Brief and Operational